So this is homework 30, part C, and I'm going to be explaining how water evaporates through the flow of nitrogen over top and how they react together. So let's first draw what this looks like. So we have a container pool with water, and over top of the pool we have a screen and the flow of nitrogen over top. So we first start this by explaining Fick's law, which is molar negative molar, not molar, the diffusion coefficient, which is like based on whatever certain element. It's like a constant for each different element multiplied by the gradient, concentration gradient. Over the area, so the area, this would be L, and this would be 0. So this area would be dz. And concentration goes from high to low, or the gradient goes from high to low. So high to low, so water would go from high to low concentration, so that would be up. And nitrogen would go from top to bottom, high to low. And this area in between is a mix of nitrogen and water. So we can model concentration by moles over volume. And if we think of it as a chemistry problem, PV equals nRT. So we can rewrite this equation as N over V is equal to RT divided by P over RT. So now if we think of this, because it's a 2-component system, we could do the concentration of nitrogen plus the concentration of water is equal to the concentration total. So we can rewrite this as P over RT plus P over RT is equal to concentration total. And because of the screen, there is no pressure gradient, so that gives us only a concentration gradient. At steady state. so there's no accumulation or anything. So now if we think of the concentration, let's draw it on a diagram. So this is concentration, and this position is 0, this position is L. So this is dz. If we think about this qualitatively, we know that concentration goes from high to low. So when we think of water, we'll give it, that's the highest concentration it can be, and it goes down to basically 0 when it gets to L. And it's kind of the same for nitrogen. So we have the highest concentration at L. But it's more of a curve. And we think about this as Fick's law. Let's rewrite Fick's law. And we can model it as the concentration. So N is equal to the joule, plus the amount times the moles total. And N total is represented as NH2O plus N nitrogen. And nitrogen is equal to 0, because when we think about concentration from going to high to low, it does go down all the way to the water, but it doesn't penetrate. It just stays on the surface, so it has to go back up. So if we think about it like as a fish in a river, the water's flowing, but for a fish to stay in one position, it has to go against the current so it stays in the certain position. So they cancel each other out. So that's how it works for nitrogen's concentration. This is homework 3, part C, part 2. Now we're going to calculate molar flux with these constraints. So, or these variables. So it's the same problem as before. So let's rewrite Fick's law. JH2O is equal to negative concentration times diffusion coefficient times DYH2O dz, the gradient, the concentration gradient. Now, molar flux H2O is equal to negative P over RT is equal to the negative GH2O plus YH2O over NH2O. Let's join these equations. So H2O is equal to CD YH2O dx plus YH2O NH2O. Now let's simplify these. So H2O 1 over Y H2O is equal to negative CD YH2O over DZ. And we can simplify this further because we know that concentration is P over RT, and we're going to just put the D. We're doing it 1 to 2, component 1 to 2, times DYH2O over DZ. And now we're going to integrate, and we're integrating the first side because it's the distance, so it's 0 to 1, and NH2O is constant. No, we're not integrating yet. No, we're not integrating yet. We're going to differentiate or differentiate these, yeah. So it's going to be NH2O DZ is equal to negative P D12 RT times DYH2O over 1 minus YH2O. And we can put this over 1 DYH2O. Now we're going to integrate 1 to 0, and this is constant. Equal, and this is constant pressure RT, integrate 1 over 1 minus Y H2O dy H2O. And the limits that we're going to set this side equal to is the molar, the mole fraction. So we know that P total is 1 e to the 5th PA Pascal, and we can calculate pressure of H2O by either looking it up or using Anton's or the Clausius-Clapeyron equation and calculating it if you can't Google it. But this value, after Googling it, is 12 to the 3rd, and we just take the fraction of this, and it becomes, the mole fraction of it is 1.2. So we're doing it from 1.2 to 0. So now we integrate, and it becomes NH2O 1 equaling negative PD12 over RT, and we know the integration of 1 over the fraction of 1 over something is the natural log of it's 8.1 over 0.88. All right. And now we just fill in. So the molar flux of H2O is negative 1e⁵ PA times 10 to the negative 5th meters squared per second. And then R is 8.314 joules per mole Kelvin. And temperature is 323 Kelvin. So then that gives us the molar flux of H2O 4.76 e to the negative 5th moles per meter squared per second. There we go.